what's going wrong. And the problem with this is that, yes, we have some test input, but in a test system you have multiple test inputs. And by naming the test input something helpful, we can figure out why things aren't working. So to show you that, I'll run my simple test system for this. So you'll see that immediately my program is dumping out a whole bunch of stuff in the console for every test that's failing. Now the ones at the top are fairly complex inputs. It's the solutions of previous assignments we've done that were also assembly files. So as we're going down, you'll see that a lot of these things are passing because they're implemented properly. Alright, so I'm going to cancel it there. You notice that this one failed. And by making very specific, small test cases, we're able to isolate piece of functionality. So the point of this test, simple LIS, is to tell me whether that specific command is working correctly or not. And because this command is failing, I can tell that the output is not correct. So if I open up the code for this, hopefully not Dave. There you go. Don't worry, I don't see that. Just go on. It's not a big deal. There you go. Okay, so we know that the problem has to do with lists. So notice that there actually is an extra bit being set here. So again, the way that I go to identify which bit that was is by looking at the diff output. I happen to know which one it is because I put this bug in here for this purpose of demonstration. So I'm going to rebuild the executable. It's using make, by the way, also a utility. And then you see if I run my test again, then everything should be passing. See? So now I know that that specific one bit set was the source of the problem, because now all my other tests are passing. So basically, to build a test system, you have to have a way of running the tests. So that's the run step. You have to have a way of verifying their output is correct. It's verified. And you have to have some reporting system that tells you whether it's working correctly or not and why. Now, the example I gave you of using diff works well for when you know that you're given valid input and you have to test against. You'll notice that some of these output tests are saying they pass and then saying bracket the error. The reason that those are still passes is because the program is expected to error on the conditions. Now you can't exactly do a diff on that because all you're checking to see is whether or not the output is erroring, or so the input is erroring or not. So what I'm doing here is I'm running the input against my assembler and the provided one and making sure that either they both error or neither of them error. If only one of them are erroring, then one of their behaviors is wrong. So yeah, so the goal of your test system should be to provide you as useful feedback as you possibly can. So one of the things I didn't build into this test system, but I had built into a later one, is the ability to run individual tests. The thing is, if you have a bug in one test, you don't want to have to run the entire suite every time just to check when you fix that one test. So, not on this one, but on my code for 7, 9, and 10, I not only have the ability to run my normal tests, which is a little different here. It takes a little while to spin up, but honestly, for testing this many things, it's not that utility. So you see that these are fairly complex tests. I'll take a look. I'll show you them a little bit. Basically, what I'm doing here is I give it a WL input, then it converts that to assembly, and then the test suite will run a set of inputs against the compiled assembly file and make sure it works. Because in this specific case, you cannot predict what the assembly output of your program will be. Because then as soon as you optimize it, all of your tests will fail. What you're really seeing is, does the thing it compiled to work? Okay, so my point that's talking about here is, you want to have the ability to run specific tests. So say I only wanted to run tests that involve simple multiplication. Then in this specific utility, I have a command line thing that lets me do this. So now it'll only run tests containing the word times. So now I know that times by itself. So if times is broken, I only want to run those ones. And then after all the tests have passed, the ones I'm specifically focusing on, then you want to run the whole suite, again to make sure you didn't break anything. So the entire code for this, or for an earlier version of this, is up on GitHub. So all the presentation stuff, if you go to github.com/leap, being, and then go to give me your knowledge, then the only folder in there will have this information. I realized in the presentation that some of this information is wrong. Let's update. This should not be .asm, it should be java.asm. But anyway, there's instructions on how to install the test system I'm talking about here. But I'll just give you a quick look inside. So, the set of test cases looks like this. And I'm not going to be providing you with my entire test suite. I'm providing you with a test system. Because everyone should be running their own test cases, and because I'm fairly sure the academic dishonest gave you own test cases. So, here's an example of test case for this specific system. This is a little more complex, like I said. I can't just pass it just an input because it doesn't test anything. So, the format of this file looks like this. It consists of the input of the actual program, so that's the int wing, etc. there. A flag specifying whether this should compile correctly or not. For instance, in another input, I have int a, int b, return c. In that case, value will be false because I'm expecting my my code generator to error out because it's not valid context. And then for each of the things here, these are the trials. So each trial is a set of input that I pass to the actual executable and make sure it's working correctly. And then the return value is what I'm expecting to return. This also has the ability to specify output, but for assignment 9, up until the last problem, you aren't dealing with console output anymore. So that's a simple breakdown of test systems and what kind of things that might be useful for if you're working on your own CS assignments. Now I'm going back to the slideshow and talking about test-driven development. So test-driven development is a very simple concept. Basically, the entire concept is that you write a test before you implement the functionality. This seems very strange, but it makes a lot of sense as you get used to it. So, to best explain this, I'll talk about test-driven development mantras. Mantra is red, green, refactor. What this means is red. You write a test and you make sure it fails. This is the part that confuses people a lot, but it's very important. I'll explain that in a second. Green means you write the code that implements a piece of functionality and make sure it makes the test pass. And the last step is refactor. Refactoring is probably the part that most people tend to skip, and I definitely do a lot of the time too, because we're never coming back to this code. As a general practice, it's good once you have working code, make it so that it's in good quality. So by refactoring it, what you're doing is you're making it more readable and you're making it maintainable by others. Going back to the idea of red, green in that order, the reason why you do this is you want to make sure that your code is the reason why it's passing. If I write a test after the fact, I have no idea whether the thing I implemented or not was the thing that makes it pass. Now, in fairly simple CS assignments like this, it's kind of trivial to say, yes, obviously that's what is making it pass. But in much more complex examples, either the functionality might already be implemented, or your assumption might be wrong about why it doesn't work. So, why should you use test-driven development? The thing of a test is that they describe the behavior of your program. You should be making yourself describe what your program does before you implement the functionality. It helps you think through a lot of the edge cases before you start coding. Because how many times have you started working on code, and halfway through going like, I didn't think of that. Because you don't need to force yourself to look at it beforehand. By writing all the tests and the edge cases before you start coding, you know that you're going to have to think of these things while you're coding. So that means writing every piece of functionality, you should be writing the simplest possible test you can think that tests that piece of functionality. This helps a lot later when you're trying to identify bugs. It also aids in incremental development. So what incremental development is trying to add on a very small amount of functionality at a time. Don't do code bombs. Code bombs is where I write 300 lines and then hope it works. Saying I'll do it right the first time, while it may occasionally work, is not a good idea. So incremental development is the idea that you choose a very small piece of functionality you want to implement, then you write a test for it, and you implement the bare minimum to pass that test. And by refactoring that bare minimum, you're making it so that it's modular and you can be extended to work on more things. The last reason why you should do test-driven development is, like I said, it helps test your assumptions. You should know when you write a test and it fails, you should know exactly why and how it's failing. If you write a test, for instance, that you're expecting to implement functionality for, and it passes when you're expecting it to fail, or it fails when you're expecting it to error, so I'll just quickly go over this. Failing means that your code is running and doesn't crash or doesn't error out. However, it's